In this video, we will examine the current consumption of car infotainment SoC core and CPU rails, discuss SoC high current power supply design and critical output measurements, and check the CPU thermal throttling behavior at high ambient temperatures.
Hello everyone! In this video, I will explain the design of the low voltage high current rails of the CPU and GPU of this MediaTek car infotainment evaluation board.
Let's look at the power requirements of the MediaTek SoC. The MT2712 SoC is available in different SKUs. The higher power version has 6 high-frequency processors. Lower power versions have less processors and run at lower frequency. There are 3 high current rails: the core rail for the GPU and video processing, the BCPU rail for the ARM Cortex-A72 processors, and the LCPU rail for the ARM Cortex-A35 processors. The current consumption of the processors in the SoC is to a large extent caused by the charging and discharging of the parasitic capacitances of the numerous switches. The higher the switching frequency and the more switches are active, the higher the current consumption. Here I measure the current in the MT2712 EVB core rail. As you can see, the green current waveform is very dynamic and has very short, fast current pulses, especially when the screen is dynamic. The PIMIC needs to ensure the core voltage stays within the operation tolerance window, so tight regulation during load transients is very important. For powering these high current rails with fast changing loads, we use the RTQ2134 PIMIC. The basic building block of this IC is a low voltage ACOT buck converter, which runs at 2.1 MHz, has 5 amp current capability, with remote output voltage and ground sense, and has I2C control. One of the key points of this converter is the very fast control loop. It uses Richtek's advanced constant on-time ACOT topology, which includes a PSR ramp for stability and a frequency locked loop for constant average switching frequency. During steady-state switching, the error amplifier output voltage is compared to a PSR ramp in order to stabilize the loop when using low ESR MLCC output capacitors. The frequency locked loop slowly adjusts the on time to keep the switching frequency within the 2.1 MHz design tolerance range. During fast rising load steps, the on time stays fixed and the control loop quickly reduces the off time. The resulting burst of on-time pulses will quickly increase the inductor current to match the new load current value. This fast step response will minimize the output voltage sag and soar during fast changing loads, which is ideal for processor power supply applications. The RTQ2134 PIMIC integrates 4 of these 5 amp ACOT buck converters. The input voltage can range from 3.3 to 6 volts, and the output voltage can be programmed from 0.3 to 1.85 volt with high accuracy. There are 3 configuration versions: 2+1+1, where 2 5 amp channels are combined into one 10 amp channel; 2+2, where 4 5 amp channels are combined into 2 10 amp channels; 4+0, where the 4 5 amp channels are combined into one 20 amp channel. Lower power SoC versions like the MT2712H can be powered by a single RTQ2134 PIMIC. In this case, the 2+2 phase version is used to power the core and the BCPU LCPU rails. The SoC controls the buck converter via the I2C bus. The high-power MT2712S SKU needs the most current and is powered via 2 RTQ2134 PIMICs, 2 dual-phase rails for the core and the BCPU, and 1 single-phase rail for the LCPU. This configuration is implemented on the MT2712 EVB. Let's test the performance of the RTQ2134 PIMIC by means of the RTQ2134 EVB. We will check the combined two-phase 10 amp channel. I will use the Richtech RAN board to control the I2C bus of the PIMIC. For testing the load transient capability, I will use the Richtech fast load transient tool as a dynamic load and a variable resistor as static load. I will measure the converter load current, the output voltage and the two-phase switching waveforms. The input voltage is 5 volt. After switch on, I will connect the RAN board to the PC to start the RTQ2134 GUI program. The default startup conditions are defined by the OTP programming of the RTQ2134 version. In this version, the default startup conditions is 1.0 volt output and pulse skip mode for enhanced efficiency at light load. You can see that only one phase is active and it operates in pulse skip mode. When I increase the static load, you can see that the frequency of the active phase increases. Above 0.6 amp load, it operates in CCM continuous conduction mode at 2.1 MHz. Above 2.8 amps, the other phase also becomes active to increase the current capability and improve the load transient response. When we zoom in, you can see that the two phases operate 180 degrees out of phase, which reduces the input and the output ripple and EMI. When the load reduces, the second phase is switched off again, and at light load the converter goes into PSM mode. When I now activate the load transient tool with a load step from 1.5 amps to 5.8 amps, you can see that phase 1 is always active, but phase 2 only becomes active during the load pulse. The output voltage shows a large voltage dip because it takes time to activate the second phase. For these kind of situations, it is better to force the two phases to be active over the entire load range. Here you see the RTQ2134 GUI tool, and in the lower window it shows that the I2C connection is successful. The GUI lets you adjust many parameters like output voltage setting, DVS slew rate and soft start slew rate. Let's set the converter operation mode from auto PSM mode into forced continuous conduction mode. As you can see, the two phases are now both active all the time. I now reduce the pulse load duty cycle to show the pulse load response more clearly, but you can see that the pulse load current rising slew rate is a bit slow. This is caused by the inductance of the load transient tool lead wires. For ultra-fast load step slew rate, it is better to reduce this inductance by using thick wide conductors between the load transient tool and the buck converter output. You can see that after using the low inductance wires, the load step is much faster. The rising edge rise time is now around 800 nanoseconds, which resembles the SoC load speed. When we make a single shot measurement, you can clearly see the ACOT loop increasing pulse frequency during the rising current step and reducing the pulses during the falling load step. The voltage sag during this load step is around 30 mV and the voltage soar is around 40 mV, which is quite okay for an SoC supply. Voltage sag and voltage soar of ACOT converters during load steps is related to the load step amplitude, input and output voltage, inductor value and output capacitance value, and the maximum and minimum duty cycles that the converter is able to reach during the load transitions. Reducing the inductor value or increasing the output capacitance can reduce the voltage sag and soar. Dual phase operation effectively halves the total inductor value, so dual phase operation will reduce the voltage sag and soar by a factor 2 compared to single-phase operation. The SoC can dynamically change the supply voltage during operation by means of the I2C-controlled digital voltage scaling function with 5 mV resolution. Let's change the voltage from 1.0 to 1.2 volt. You can see that the voltage rises with a certain slew rate, which was defined by the RSP up setting, which was in this case 16 mV per microsecond. The falling slew rate RSP down setting is 4 mV per microsecond here, so when stepping from 1.2 volt back to 1.0 volt, you can see that the voltage drops much slower. Another cause for current consumption in the SoCs is leakage current of each switch. This leakage current rises exponentially with temperature. In automotive environment, high ambient temperatures should also be considered during the design stage, as the car internal temperature can become very high when the car is out in the sun during summertime. Let's have a look at the current consumption of one of the processor rails of the MT2712. I have mounted a thermocouple to the MT2712 SoC, and I measure the average current via a 1 milliohm sense resistor in the B CPU rail, so 1 millivolt equals 1 amp. I'm running the ARM Cortex-A72 CPUs with a fixed stress test load. Initially, the average current is around 3.5 amps. When I now blow hot air on the SoC, you can see that the average current slowly increases. The curve shows an exponential behavior. But at 85 degrees C, there is a sudden drop in current. This is because the SoC has an internal die temperature sensor, and it will reduce the processor clock frequency at higher temperatures, thereby reducing SoC current consumption to avoid excessive SoC dissipation. At high temperatures, the RTQ2134 PIMIC could also overheat due to the higher SoC load and higher PCB temperature. For this reason, the RTQ2134 also includes a temperature sensor. Let's test this by heating up the RTQ2134 IC with hot air. We will now set the GUI in continuous I2C register reading mode. At 110 degrees die temperature, an interrupt will be set to tell the SoC to read the hot die register value, which, as you can see, has changed from 0 to 1. The SoC now can take measures to reduce the loading current by reducing the clock frequency as well.
I hope you now have a better understanding about electronic power design for automotive applications. Please stay tuned for more interesting videos at RichTech, your power partner.